David Smith here with one more Flipped Classroom math video. 3 tips before we start. First, remember you can speed up or slow down the playback if that helps. Second, you can pause a video at any point in time and catch up on your notes. Third, you can turn on the captions and watch my words go by on the bottom of your screen. Today's topic is cubic modeling. So we're going to use cubic functions or power functions to model real-life situations and answer some questions. So first off, let's orient to this particular problem. What we have is a open box that we're going to make from a sheet of cardboard. So basically we're going to take that sheet of cardboard, cut the corners out, fold the sides up, and we'll have an open box like a tray, something like that. Now we have some specific measurements here. It's made with a cardboard sheet measuring 10 centimeters by 12 centimeters. And then squares are cut out of the corner so it can be folded up into a box. And so let me show you what that looks like. Okay, here's our sheet of cardboard, 10 centimeters by 12 centimeters. And then we've cut out these little squares in the corner so we can fold the sides up and make our box or our tray. And so these are length X. And they're squares, so we know that both of those are X. So, first step, what are the dimensions of the tray? Okay, because we're going to try to maximize the volume of this box, and we need to think about some dimensions that will do that for us. So, what is the length of the tray going to be? And what is the width of the tray? In other words, the sides are folded up, so they're not part of the length and width. So you have X. You don't know what X is, but you can write an expression for length and width. So go ahead, pause the video and do that. Okay, you'll see that we subtract X from the length 2 times, because I have X here and I have X here. So the length of the resulting box or tray is going to be 12 minus 2X. That's twice these 2 corners that got cut out and folded up. And the same thing happens with the width of the box. We're 10 centimeters from corner to corner of our sheet, but we're going to cut out X twice from that width, so we're going to have 10 minus 2X. Okay, now we can write a formula for the volume of this box. So think real hard, pause the video, and do that. All right, let's see how you did. Now, I know you remember, volume is just length times width times height. Once we fold this box up, this X is the height of our box. So volume is going to be height times length times width. And that is a cubic function. If I were to expand out that expression there, I'd end up multiplying X by itself 3 times, which would give me an X cubed term in my function, and then I would have a cubic function. So now, when we do cubic modeling, one of the most useful things that we do is we figure out where maxima or minima are. Now, if we're making this box to say hold rice, and we want it to hold as much rice as possible because that would give us the greatest bang for our buck. We used a piece of cardboard here. We want it to hold the most rice it can. So what we need to do is figure out what this X is. How far in do we cut our squares to maximize the volume? So how might you do that? All right, in case that 3D problem was stumping you a little bit, I went ahead and I sketched our box in 3D. And you can see here, here's our height from where we cut the squares out. That's X. Our width is 10 minus 2X, and our length is 12 minus 2X. So that's the box drawn in 3D for you. And then here's our function written in function notation. Volume as a function of X. That's as a function of the length of that little square we cut out of the corners of our box is going to be X times 10 minus 2X times 12 minus 2X. So the question I just asked you was, how might I figure out how to maximize the volume for that box? So think about that for a minute. If you know what to do, go do that. Okay, so the way to do this is to graph it, because the maximum will show up as a downward turning point. If you graph volume on the vertical axis on the dependent variable as a function of X, you'll find that your graph is going to have a peak, and that's going to be the max volume. So go ahead and get out your calculator and put this function in there and see if you can come up with the maximum volume as a function of x and then what that x would be. All right, let's take a look at the graph here. So check this out. This is from the calculator, and I just graphed x on my horizontal axis, and then I graphed v of x, or y, which is volume, okay? Because that's this expression. The x term goes here, and then that determines the volume. And that's the equation that we developed for the volume of this box. So on the graph, you can see that when x is 0, we don't have a box. We just have a flat sheet. We can't fold it. We have to cut out some corners. Now, as x increases, once x hits 1.81 centimeters, we hit our peak. Now, you can find that on your graph using your calculator, using the trace function, and that'll tell you that the max volume of 96.8 cubic centimeters occurs when that square that you cut out of the corners is 1.81 centimeters by 1.81 centimeters. As soon as that square starts getting bigger, volume is going to go down again. Now check this out. We're going to hit the x-axis. What does that mean? That means volume is 0 when x is 5. Now, does that make sense? Think about it, look at that diagram, and see what you think. Okay, check this out. When we cut a 5-inch square, the width of the box goes to 0 because the piece of cardboard is 10 centimeters. If I cut 5 out of each corner, suddenly I'm folding everything all the way up. I don't have a box. I have a width of 0. With a width of 0, I'm going to have a volume of 0. Now, as the square gets bigger, actually, you can't do it. So the mathematical function continues on because that's just math. We can go negative, etc. So, for example, if I could cut a 5.52 centimeter square out of the corners of the box, which I can't, but if I could do that, my volume would be negative 5.51 centimeters cubed. But again, that doesn't really make sense in terms of our word problem. Pretty much the graph, as far as our problem goes, just stops here. The rest of it is certainly mathematics, it's certainly valid mathematics, but it doesn't apply to our situation. Once we pass a 5 centimeter cut out of the corners, the equation no longer models reality. And then we get back to 0 again when that square is 6 centimeters on a side, and that's because now the length is going to be 0, the whole thing is going to be 0, so we have a 0 volume. And then as we cut bigger and bigger squares out, the mathematics, the function, is going to give us a nice high volume. In fact, it's going to go on forever, but again, does not make sense in terms of our situation. So to go all the way around the circle and summarize, what we did is we had a situation, we were asked to maximize something, and we came up with our cubic function that it shows volume as a function of x of this little square that we cut out of the corner of a flat sheet of cardboard. Then we took that equation and we put it into the calculator, made a graph, found the maximum. Again, that's the volume. We're plotting volume against the size of the square that we cut out, and the volume is greatest when that square is 1.81 centimeters, and that gives us a volume of 96.8 cubic centimeters. That's the maximum. Now that you've watched the video, take a moment to jot down any remaining questions so you can ask them at our next class. If you want, you can come back and watch the whole video again if that helps deepen your understanding. If you enjoyed the video, please click like or subscribe.